Okay, so today what we're going to be doing is we're going to be looking at some word problems involving kinematics, okay, study of motion and some of the mathematical relationships between different aspects of motion. The packet that I've given to you has got several problems. We're going to be focusing on a few in particular, and then as we get into more complex things, I'm going to be introducing you to your new best friend, which is the Big Five. Either you're going to love the Big Five or you're going to hate the Big Five, but after today, your world will never be the same because of the Big Five. So let's first of all just kind of recall our definition of displacement, okay? For displacement, remember what we're looking at is we're looking at the difference in position from wherever you started. Now, how you got from point A to point B is not really important. The only thing when you're looking at displacement is what is your total distance from your final position to your initial position. Okay? Displacement is symbolized as delta x. Sometimes it's symbolized as delta y, as we'll see when we get into projectile motion if we're looking at the up and down component to motion. But most of the time, delta x, or just change in x, as though you've got a graph that is on an x-axis and you're looking at your difference in position there. Okay? So what I'd like to do is I'd like to look at problem number 2. Wow. Okay, where a child walks 5 meters east, then 3 meters north, and then 1 meter east. So I want to know what's the magnitude of this child's displacement. To solve this, the easiest thing to do is going to be to make yourself a diagram. So I'm going to just kind of make one off to the side here. I'm going to say that, okay, from the starting point, the kid's going to go 5 meters east, 3 meters north, and then 1 more meter east. Okay? So my starting position is right here. My final position is right here. Now, could I change this diagram around a little bit to make it a little bit easier for me to find what this resultant vector is? Because remember, when we add vectors, it doesn't really matter what order we add them in. Okay? So I could take this 1 and I could add it to my 5, right? Yes. And so I could take this whole thing and I could actually have 6 meters going east and 3 meters going north. We're going to pretend like that's a right angle because that would let us make a right triangle, right? Okay? And so if I want to find the magnitude of the displacement, what I'm looking for is the size of the hypotenuse right there. What's a really easy way that we can find that? Good deal, Pythagorean theorem. So let's do that. Let's go 6 squared, which is 36, plus 3 squared, which is 9. 36 plus 9 is what, 45? Yes. Okay. Let me take the square root of 45. I'm going to go ahead and just get a decimal for that. So square root 45. And I get something like 6.708. I'm going to call that 6.71. So I can say that my displacement, A, is going to be 6.71 meters. Now, what's the direction of the child's displacement? So here, what I'd like to do is I would like to find, all right, so what's the angle that we're making there? Okay, going up from my x-axis. So how can we find that angle? There's lots of different ways. What do you guys want to do? Use a trig function of some kind. Okay, yeah, we can just do tangent if we want to. So we'll call this angle theta, and so we can say that the tangent of theta is equal to opposite over adjacent, so it's equal to 3 over 6. So what I can do is I can go second tangent. Now 3 over 6, I can just do 3 divided by 6. I know that's going to be 0.5, but I can do 3 divided by 6 in my parentheses. And I get an angle of about 26.57. Okay, so B, I'm going to say it is 26.57 degrees. Okay. I'm leaving 1 and 3 for you because 1 and 3 are quite a bit easier than 2, so I don't think you're going to have any trouble messing with those two. But does anyone have any questions over what we just looked at there? All right, cool. So let's come down now and let's look at the next section, which is speed and velocity. Okay. So can somebody recount to me what's the difference between speed and velocity? Right, one has direction. Velocity has direction. Velocity is a vector, whereas speed is just a scalar. Okay. And so if we're talking velocity, usually what we're talking about is the variable v. Okay. If you're talking about, that's a square root, that's not what I'm looking for. If you're talking, I did it again. I need to stop talking and writing at the same time. If you see a symbol with a V with a little line over it like this, okay, this right here is average velocity. Okay? An average velocity, the way you find that is equal to, you take your final velocity, vf, you add your starting velocity or original velocity, vo, and then you divide by 2. And that's on your formula chart that we're going to look at here in just a minute. So you don't have to write that down. It's already there for you. Now speed or velocity, either way, you're talking about two things you need to know for that. Okay? Think about the way that we express speed. Speed in your car is measured in what? Miles per hour, right? Okay? And so there's two things you need to know in order to determine speed. You need to know miles, which is a unit of what? Miles are used to measure distance, thank you. And then hours are a measure of what? Time. So in order to tell the speed of anything, you need to know the distance it's covering and the time in which it's covering it. So another word for distance, if we want to make this a vector thing, then we could do displacement. And so you could look at velocity as being equal to the displacement, or change in x, divided by the change in time, or delta t. Okay? And we can kind of simplify that too. We can also just kind of say delta x over t, okay, because we're going to assume that time is passing. So anyway, let's look at problem number 4 here. If the child from problem 2 completes his journey in 20 seconds, what's the magnitude of his average velocity? Okay, well, let's look at this kid up here and let's see what we know about him. Okay, we know his displacement. Okay, his total displacement is 6.71 meters. So we can say down here that delta x equals 6.71 meters. We can say that his time is 20 seconds. So if I want to find his velocity, what I can do is I can take his displacement divided by his time. Now, something I don't know here, well, we can make assumptions about like his starting speed. We can say he's starting out at his speed of 0, and we could just kind of conjecture on what his final speed would be, but here we don't really need to know that. All we need is total change in displacement, which is that, and his total change in time. So if we go 6.71 divided by 20, turn on a little bit, then I get that he is going 0.3355. I could say about 0.34. What would my units be here? Meters per second. Okay. So there again, in the unit, I've got distance component and I've got time component. Okay. Now, since it's if I wanted to get like his direction in there, then I could say 0.34 meters per second at 26.57 degrees. Okay, and that would work. Any questions about that? Not too tough? I'm going to leave number 3. I'm sorry, I'm going to leave number 5 for you. Let's flip the page. Because now it's going to start getting fun. We're going to take a look at acceleration. Okay. Now you did a lab last week where you were looking at acceleration due to what? Gravity, exactly. Acceleration of an object in free fall. We found that gravity's acceleration is equal to about 9.8 meters per second squared. Okay, meaning for every second that something's falling, it will accelerate by 9.8 meters per second. So that kind of acceleration is constant acceleration. And so what we're looking at here is we're looking at constant rates of acceleration. Okay, constant rate of acceleration is symbolized by, not too surprisingly, letter A. Okay. And here things start getting a little bit complicated, but here also I'm going to introduce you to this guy, which is the fabulous Big Five formula sheet. Now these Big Five, I don't know who called them Big Five or why they got the numbers that they got. I just know that for all kinds of situations, these 5 formulas come in super duper handy. Just kind of show you how these work. Delta x, you've already seen, that's displacement. V is velocity. Delta t is change in time. T is time itself. When you've got an xf and an x sub o, that's final position, original position. So what else on here? What are some letters that we haven't talked about? Anything? No, that's totally it. So these right here are all different ways that these variables are related to each other. And out to the side here, this helps you figure out which of these Big Five formulas you can use in a given situation. Because you don't have to know every variable in order to make these work. In fact, for each one of these, like Big Five number 1, you don't have to know your rate of acceleration. You just have to know that acceleration is constant. For Big Five number 2, you don't have to know displacement, and so on and so forth. I like to think of these like tools in a toolbox. Okay? If you've ever done any kind of handiwork, if you've ever tried to fix something, you know that sometimes if you've got something that's broken, you go to your toolbox. Well, there's a whole lot of tools in there. Some people are going to grab a screwdriver to get a certain job done. Other people are going to grab the biggest hammer they can find, and they're going to beat on something until it works. Okay? Other people might choose to use a wrench. There's no wrong way to do a certain job. Just like with a lot of these motion problems, there's no wrong tool to choose. You can make any of these work in different situations. The big thing that's going to come with practice is figuring out which ones are you more familiar with, and therefore which ones come more naturally for you to use. Okay. Some of you are going to love this. Some of you it's going to drive crazy that there's not just a single way to get something done. But we're going to jump in and we're going to take a look at this. So look with me at problem number 8. Remote control car is driven along a straight track at 2 meters per second. The child controlling the car then activates the toy's turbo mode so that 3 seconds later the car's speed is 3.2 meters per second. So find its average acceleration. First thing I want to do in any kind of motion problem like this is I want to define all the variables that I can find in the problem. So what would 2 meters per second be? It's going to be a velocity, right? But is it going to be average velocity, starting velocity, or final velocity? Starting. So I can say that my v sub o is 2 meters per second. Okay. Car speed after 3, what is 3 seconds going to be? Okay, so t is going to equal 3 seconds. And what is 3.2 meters per second? That's final velocity, so v sub f. Okay, so I need to find average acceleration. So what I'm going to do is I'm going to look at my big 5, and I'm going to see which ones include VO, VF, time, and acceleration. Okay. Well, there's VF, there's VO, there's acceleration and time. Or I can also look at that as change in velocity is equal to acceleration times time. So let's look at big 5, number 2. Okay, I'm going to want to rewrite it to get acceleration by itself because that's what I'm looking for, but I'm going to start by writing VF equals VO plus AT. All right, so if I want to algebra this formula before I start plugging in any numbers, how can I get A by itself? What's the first thing I want to get rid of, the T or the VO? The VO because it's further away from it. And algebra is kind of like an onion. You want to start peeling from the outside and work your way in. So I can subtract VO from both sides, right? So I can have VF minus VO equals A times T. Now how can I get rid of that T? Divide. So I can do VF minus VO over T is equal to acceleration. Okay, now I've got my acceleration by itself. I can take my numbers and I can start plugging them in. So when I plug this in, I'm going to do 3.2 minus 2 divided by 3. And if you're doing this all in one operation, you want to use parentheses on the top part so that you don't accidentally divide by the wrong thing. So I'll do 3.2 minus 2 divided by 3. And I get an answer of 0.4. So I'm going to have 0.4 meters per second, or 0.4 meters per second squared. That meters per second squared comes from the fact that I've got, that's in meters per second, so I've got meters per second being divided by seconds. Okay, and that's my answer. What you're going to find look at number 9 real quick. Number 9 is asking something about the same car, only it says that it's slowing back down in 2 seconds. So for this one, you're going to do a very similar kind of thing, except just kind of as a hint, your answer is going to be negative acceleration, because we're still defining positive as the direction that car was traveling to start with. And since it's slowing down, the acceleration is happening in the opposite direction. That's an awful lot to chew on, but how are you guys feeling? Does anybody have any questions about number 8? It's a very quiet room today. Well, let's keep on going. Let's skip down to our next section here. Look at number 10 for me. Okay, particle moves along the x-axis with an initial velocity of 4 meters per second and constant acceleration. After 3 seconds, its velocity is 14 meters per second, so how far did it travel during this interval? Let's start, before we even worry about formulas, and let's figure out what variables they give us here. Okay, so what is 4 meters per second? That's VO, so VO equals 4. I'm going to dispense with the units just for right now because I'm not too worried about them. What's 3 seconds? Okay, so T equals 3. Okay, what's 14 meters per second? Okay, that's VF. Okay, and it wants us to find what? How far did it travel? So what variable are we missing? Okay, so we're looking for delta x is the one we're hunting for, right? Okay, so what we want is we want to find a formula that involves these 4. Now, what's the one variable that we haven't mentioned here? A. So it doesn't use A. So that's a clue to tell me which big 5 I need to use. I need to find the one that doesn't use A, which means I'm going to be using big 5 number 1. Okay? So my displacement is going to be either my final position minus my original position, or it's going to be my average velocity times time. Now, I don't have average velocity, but what do I have? I've got my final and my starting. So can I get average velocity? Totally. I'm going to add those two together and divide by 2. So for starters, I'm going to do average V equals VF plus VO divided by 2. So it's going to be 14 plus 4 divided by 2. 14 plus 4 is 18. What's 18 divided by 2? Okay, so average velocity is going to equal 9. Now I'm going to look at big 5 number 1, and I'm going to see that my displacement is equal to average velocity times time. So delta x equals average v times t, which equals 9 times 3. So how far did it move? Okay, so delta x equals 27 meters. Again, that's a lot of stuff, but is any one step in there really complicated? What do you think is the hardest part about doing a problem like this? Losing track of stuff, keeping track of what number goes with what thing. What'd you say? Okay. All right. So on this one, we did have multi-steps, right? We had this first step where we had to find the average velocity so that we could use big 5 number 1. And then the second step where we used big 5 number 1, right? But again, that's something that's going to come with some practice. Look at number 11. Car is initially moving at 10 meters per second. and accelerates at a constant rate of 2 meters per second squared for 4 seconds in a straight line. How far did the car travel during this time? Let's get down what they give us. What is 10 meters per second? That is VO. Okay? Constant rate of 2 meters per second squared, what's that going to be? That's A. Good deal. So A equals 2. 4 seconds, what is that? T equals 4. How far did the car travel? So they want us to find delta x again. This time, though, they give us acceleration. What's the one variable we don't have? Vf. So if you look at your Big 5 chart, we're looking for one that doesn't use Vf. So Big 5 number 3. And you're like, what voodoo is this? It's really not bad. So delta x equals VOT plus 1/2 AT squared. I'm going to copy that formula over. Delta x equals original velocity times t plus 1/2 of acceleration times time squared. Now I know all of those numbers, right? So I can just start plugging them all in. So I'm going to go VO times t. So that's going to be 10 times 4 plus 1/2 of 2 times t squared, so 4 squared. I can either start plugging that into my calculator or I can even further simplify. What's 10 times 4?
40.
Okay, it's going to be 40. What's 1/2 of 2?
1.
1, okay. What's 4 squared?
16.
So what's 1 times 16?
16.
Okay, 40 plus 16 equals what?
56.
Okay, so the car traveled in those 4 seconds, it traveled 56 meters. All right, shall we look at a few more? Why the heck not? Let's at least look at number 12 and number 14, and then I think I'm going to stop throwing new math at you guys for one day. Number 12. Oh, this is fun. A rock is dropped from a cliff. It is 80 meters above the ground. If the rock hits the ground with a velocity of 40 meters per second, what acceleration did it undergo? So, what variables do I have here? What is 80 meters? Okay, so delta x equals 80. Okay, it hits the ground with a velocity of 40 meters per second. So, what would that be? It's going to be Vf equals 40. Do I know VO?
No.
Really?
0.
Why 0?
Just
Right, because I just haven't dropped it yet. So VO equals 0. All right. Now I don't have time, right? And I'm looking for acceleration. Now, we're going to pretend that we don't know the acceleration due to gravity. But this might be a nice common sense check. If A ends up equaling decently close to 9.8, then we can assume that this rock was dropped somewhere on planet Earth, right? Okay. So I don't have time. So if I don't have time, I have to use Big 5 number 5 because it doesn't use time. So Vf squared equals Vo squared plus 2a delta x. Let me jot that down. Now let's see if we can maybe simplify this a little bit. Vo is 0, right? What is 0 squared? 0. So for our purposes, we can kind of ignore this part because that part's equal to 0, right? So we can just say that Vf squared equals 2 times a times delta x. So it's going to be 40 squared. Now wait, we're looking for a, right? I don't want to start plugging numbers in yet. Let's algebra this thing out. How can we get a by itself? Well, yeah, let's divide both sides by 2 delta x. That work for you? So if I have VF squared divided by 2 delta x, that's going to give me A. So now let's plug this in. So I'm going to do 40 squared divided by 2 times 80. So, okay, 40 times 40, that would be 1600. Okay, so 1600 divided by 160. I think I can do this one in my head. I think that's going to be 10. So our acceleration, according to our numbers here, is 10 meters per second squared. Now that's decently close to 9.8. That's if you do a little bit too much rounding in your measurements and you're not using nice, precise measurements. But for that matter, if you're just having to do any of this math in your head, if you're doing anything involving free fall, which, spoiler, we're about to, it's awfully close to 9.8. 9.8 is going to give you better, more precise answers. But if you're having to do it in your head, 10 is a nice number to work with in your brain, right? Okay, we like to think in tens. We are digital beings. Do you know why digital is called digital, by the way? Has to do with your fingers. Your digits. How many digits do you have? 10. Questions on 12. Let's do 14. So for free fall, the nice thing about free fall is you can assume that your acceleration is going to be 9.8. If you're talking about acceleration due to gravity, do you make it a positive 9.8 or do you make it a negative 9.8? It does matter. It matters if you consider what direction your object is moving to start with. Okay? And let me help you with this. If you take a look at number 14, for instance, which is the one that I've got for us to do here. A ball is thrown straight up with an initial speed of 20 meters per second. So how high will the ball travel? Picture this for a minute. The ball is starting up by going up, right? So its initial VO is going to be 20, right? And it's going to be positive. What's its final velocity going to be when it stops moving up? F equals 0, okay? Will acceleration here be in the same direction it was moving or the opposite direction? Opposite direction. Acceleration is going down, so since we're making this positive, we're going to make acceleration equal negative 9.8. Could you also start by making this negative 20 and making it a positive 9.8? Sure. You're the one who gets to decide what direction negative is and what direction positive is. Just be sure that since these are going different directions, that you give them different signs. Okay? So let's talk about what we know. We know that VO is 20. It starts with a 2, not a 0. We know that VF is 0. We know A is negative 9.8. What do they want us to find? They want us to find delta x, so delta x is our unknown. What never gets brought up? Time, okay? So we can use big 5, which one? Big 5, number 5. So let me copy my formula down. So VF squared equals VO squared plus 2A delta x. Okay? So VF squared is going to equal what? 0. Okay? So we can say that 0 equals VO squared plus 2A delta x. And if we're trying to get delta x by itself, how can we do that? Okay. So we can say negative VO squared over 2A is going to give us delta x. Okay, I made a little bit of a jump there with my algebra, but did I lose anybody? Let's do VO squared, which is 20. So it's going to be negative of 20 squared over 2 times negative 9.8. What do you think those negatives are going to end up doing? Exactly. Okay. So 20 squared is 400, right? I'm running out of room here. So it's going to be 400 over 19.6. And again, if you were using 10 here, you could just do this in your head. We could do it as kind of a common sense estimate. So that would be like 400 divided by 20, or 40 divided by 2. So our answer is going to be somewhere close to 20. What is 14 divided by 19.6? Wait, I did the wrong thing. 40, not 14, but divided by 19.6. You know what? That would help, right?
Yeah, that part is.
Thank you.
That part is 20.41.
Great, and we were shooting for 20 as our rough estimate there. So 20.41 meters. Whew, look at all that math we had to do to solve that one thing. Is there any step of that that's especially difficult? So here's my pro tips, and then I will leave you alone to work on whatever it is you need to work on. Write everything down. Use lots and lots of scratch paper. I know some of you really hate showing your work. You really can't survive doing this kind of thing without writing everything out. Use lots of paper, use lots of space, be very careful and double check your numbers and whatever it is you write down. We're just about out of time. Does anybody have any closing questions or remarks? Okay. So we're going to go ahead and call it.